were doing this chapter, annihilating polynomials. So I think there were 2 theorems left which I requested you to go through. So let's see the statements of those theorems. Let T be a linear operator. Theorem 2 I think we did in the last class. Theorem 2, yeah, it was done. So let T be a linear operator on an n-dimensional vector space V, or let A be an n cross n matrix. The characteristic and minimal polynomial of T has same roots except for multiplicities. Okay. So P be the minimal polynomial of T. Let C be a scalar. What we want to show is PC is 0. If and only if C is a characteristic value of T. That's clear, right? Because if C is a characteristic value, then it of course it is a root of the characteristic polynomial. We want to show that it is a root of the minimal polynomial as well. So yeah. So let Q be a polynomial such that P is x minus C into Q. So Px is x minus C into Qx. Okay. Now clearly degree Q is less than degree P, since P is the minimal polynomial. Now Qt not equal to 0. Why? Why Qt not equals to 0? Because if Qt is equal to 0, then Q becomes the Q has degree less than the degree of the minimal polynomial, which is a contradiction. Okay. So Qt is not equals to 0. Choose a vector B such that Qt beta is not equals to 0. See, Qt is an operator. Okay. Suppose Q is of the form, Qx is of the form a1 x plus a2x square and so on, say not, then Qt is a linear operator of the form a1t plus a2t square up to a naught I. Okay. This is a minimal polynomial. This is an operator. So Qt is not identically 0. That means there is a vector which is not killed by Qt. Let's call it beta. So Qt beta is not equals to 0. Put alpha equals to Qt beta. Now see, Pt beta is 0, right? Because Pt is the 0 polynomial. T satisfies P. Oh, just a minute. Alpha equals to Qt beta, then Pt beta equals to 0. Yeah, P is the minimal polynomial of T, so Pt is 0. So Pt beta is also 0. Now they have written this. Okay. Now they have written this. T into Ci minus alpha is 0. Thus we get T alpha equals to C alpha. So C is a characteristic value of T. Okay. This means the C is a characteristic value of C. Okay. So what did we prove? We proved that if C is a root of P, that is if PC is 0, this implies C is an eigenvalue. Okay. Now we will show the opposite, that if C is an eigenvalue, P is a 0. Let's show that. Suppose C is a characteristic value of T. So say T alpha equals to C alpha with alpha not equals to 0. As noted in the previous lemma, Pt alpha is Pc alpha. We have seen it. But since Pt is 0, because P is the minimal polynomial, so this is 0. Now Pc alpha is 0. Pc is a scalar. P of C is a scalar. Is 0 and alpha not equals to 0. So of course Pc is 0. Okay. So this is done. Let T be diagonalizable linear operator and C1 to Ck be distinct characteristic values of T. Then it is easy to see that the minimal polynomial for T is the polynomial this. Okay. So what is the assumption? The assumption is that T is diagonalizable. T is a diagonalizable linear operator and C1 to Ck be distinct characteristic values of T. Then it is easy to see that the minimal polynomial of P is x minus C1 to x minus Ck. That is, the minimal polynomial of T of a diagonalizable matrix splits into linear factors. See, these are linear factors. Okay. So then, one of the operators T1, C1i sends alpha into 0. Suppose alpha is a characteristic vector. Okay. So T alpha is equal to Ci alpha for some I, right? That's what they have written. That one, so T minus Cii of alpha is 0. So one of these sends T alpha, one of these sends alpha to 0. Now suppose this I sends alpha to 0. So you can write this T minus Ci, T minus C1 up to T minus Ci into T minus T minus Cki, okay, of alpha is 0. Okay, but what is this? This is P of T, na? This is P of T of alpha, right? So see, we can write Px as x minus C1, x minus Ck, and we can write Ci at last, right? We can take this factor, suppose x minus Ci factor, to the last. Okay, so then Pt becomes T minus Cii dot T minus Cki into T minus Cii. Okay, so what is Pt alpha? This is this into alpha, and this part is 0, isn't it? T minus Ci alpha is 0 by this. So this whole thing is 0. So Pt alpha is 0. Okay. For every characteristic polynomial alpha, there is a basis for the underlying space which consists of the characteristic vectors of T. Hence, this happens. You understand the meaning of this line? They are saying that T is diagonalizable. This implies there exists a basis alpha 1 to alpha n of V such that each alpha I is an eigenvalue of T. Okay, and we have seen Pt of alpha I is 0, right? Because if alpha is a characteristic value, we have shown that Pt of alpha is 0, right? Since Pt sends each of the basis elements to 0, we can write Pt V is 0 for all V belongs to capital V. এত লেট করো না, don't be so late.
Sorry, yes,
Okay, so yeah, So Pt V is 0 for all V belongs to capital V, right? Thus Pt is 0. Okay. So Pt is 0. What we have concluded is this. If T is a diagonalizable linear operator, then the minimal polynomial of T is a product of distinct linear factors. See, watch this thing very carefully. We have proven one, that each characteristic value of T is a root of Px, where Px is the minimal polynomial of T, right? Thus, if C1 to Ck are, these are all distinct, these are distinct eigen values of T, then PCI is 0 for all I belongs to 1 to k. So x minus ci divides px for all I belongs to 1 to k. Thus the product x minus c1 to x minus ck divides px, right? This is 1. And 2, we have seen t minus c1i, t minus cky is 0, right? So annihilates T, but among all annihilating polynomials, Px has least degree, right? So Px is equal to this, okay? I should write this, but among but among chata. This implies, what does this imply? Degree of x minus c1 to x minus ck is less than deg p, isn't it? Because this thing divides px, na? This product. So degree of this has to be less than degree this. Least degree. This implies deg p is less than equals to deg x minus c1 to x minus ck, right? Thus both of them are same. Deg x minus ck, okay? So this is the minimal polynomial. Got it? We have concluded that if T is a diagonalizable linear operator, then the minimal polynomial of T is a product of distinct linear factors. As we shall soon see, the properties characterize a diagonalizable operator. That is, the opposite are also true. That if the minimal polynomial is a product of distinct linear factors, then T is diagonalizable. We will prove it in one of the later sections. So example 4 and example 5, and I expect you to see this at home. This is the Cayley-Hamilton theorem. Like T be a linear operator on a finite dimensional vector space. If F is the characteristic polynomial of T, then Ft is 0. In other words, the minimal polynomial divides the characteristic polynomial. Okay. See, this proof, I mean, the minimal polynomial divides the characteristic polynomial. Remember the statement, nobody will ask you for the proofs. But I have seen some proofs of this that uses analysis and not linear algebra. Those are very beautiful proofs. It was done by John B. Conway. Let's move on to the exercises. Tell me, 1. What is the minimal polynomial of the identity operator? Quick. This is very easy. What is the minimal polynomial? This is x minus 1 is the minimal polynomial. Okay. Now, let A, B, C be elements of the field F. Can you do 2? Can you do 2? Okay, try 2 at home. Try 2 and 3. These things you can do at home. These are computations. Okay. Is the matrix similar to the diagonal matrix? V be an n-dimensional vector space, and let K be a linear operator on V. T be a linear operator. Suppose that there exists some positive integer. This is also very easy. I think you can do this at home. Okay. If you can't, then let me know, because things that might be easy to someone and may not be that obvious to somebody. But if t to the power k is 0, that means t satisfies x to the power k, this polynomial, right? T satisfies this polynomial. But how do we prove it? How do we prove it? Rahul, how do we prove it? See, if k is less than equals to n and t to the power k is 0, you can just operate it by t n minus k, t to the power k, then it is 0 of course. But the case is when k is greater than n. If k is greater than n, then what do you do? So t satisfies x to the power k, right? This implies px divides x to the power k, where px is the minimal polynomial of t, right? Because any polynomial, if it kills t, it must be divisible by the minimal polynomial, na? So px is of the form x to the power m because px divides x to the power k. So px is equal for some m less than equals to k. Since every ch root, characteristic root of t, must appear in px, we can say that 0 is the only root of fx, where f is the characteristic polynomial, that is the ch polynomial of t. Thus fx is of the form x to the power n. Okay. Find a 3 cross 3 matrix whose minimal polynomial is x square. How to do it? How to do it? So first, t square is 0. Okay. This implies t is nilpotent, right? T is a nilpotent 3 cross 3 matrix, right? Let's see. Hello. Okay, so we will have to show that mm, we will have to find a polynomial meanwhile whose matrix is this. So T is nilpotent, right? And we have seen that a nilpotent matrix is of this form. This can be, or it can be like this, I mean the zero matrix, or it can be like this, right? We have seen it. This is of rank 1, this is of rank, this is of rank, sorry, 1 will be here. This is of rank 0 and this is of rank 2. Okay.
তাহলে মাঝেরটার মিনিমাল পলিনোমিয়াল এক্স স্কোয়ার হবে।
No, it will be 0.
হ্যাঁ,
X square can. So the minimal polynomial of this is x, just x.
হ্যাঁ,
The minimal polynomial of this is, mean poly of this is x cube, because a is non-zero, I mean t is non-zero, t square is non-zero. So x cube is the minimal polynomial. Here we see t square is 0 and t is non-zero. So the minimal polynomial is x square. Okay. Let n be a positive integer and let v be the space of all polynomials over R which have degree at most n. Zero polynomial is operator. Let d be the differential operator. What is the minimal polynomial of d? প্রিয়দর্শিনী আছে ক্লাসে? Is প্রিয়দর্শিনী in the class? আবার হোয়াটস কি লিখছে। আচ্ছা আচ্ছা এখানে সো d
দাদা
of f,
ম্যাট্রিক্সটা তো লেখা যাবে,
sorry,
ম্যাট্রিক্সটা তো লেখা যাবে মানে
yeah we
ট্রান্সফরমেশন।
will do that. So first pick up a basis of this v. This is 1x up to x to the power n, right? And as she is saying, like d1 is 0, dx is 1 to x plus 0, dx square is, sorry, 0 into 1 plus 1 into x. This is 0 into 1 plus 2 into x and so on. So the matrix with respect to beta will be 0 0 0 0 1 0 0 0 0 2 0 0 and so on. Okay, so clearly this is an nilpotent matrix, huh? This is a nilpotent matrix of rank n minus rank n n plus 1 cross n plus 1, nilpotent matrix of rank n. So x to the power n is the minimal polynomial. See, I am solving all these problems, but I know there has to be some questions like how do I know this is x to the power n is 0? This is
হ্যাঁ,
nilpotent.
এটাই আমি বলতে চাইছিলাম যে এখানে
This is
n
nilpotent.
কেন
Huh?
হচ্ছে?
So d to the power n plus 1 is 0. That's obvious. But why should it be x to the power n is 0 as nothing else? So let T v to v be a nilpotent matrix but nilpotent operator. Okay, dimension v is n and t to the power k is 0 or k less than equals to n. Okay, and t to the power k minus 1 is non-zero. So basically what we are trying to do is that we will do is so let's take v outside of car t to the power k minus 1. Okay, thus t to the power k minus 1 v is non-zero. So this set tv, this set is linearly independent. We have done this, right? We have checked this before, that this set is linearly independent. Okay, now is linearly independent. Okay, so now rank of T is, just a minute, just give me a minute. What about kernel T? TV is 0. Let's take V1 to VR belonging to alpha 1 to alpha R belonging to kernel T, such that alpha 1 R be a basis of kernel T. Okay. Okay. But that's a valid question. That why should it be exactly n? See, actually, the degree of nilpotency is equal to the rank of the matrix, but I am trying to prove it. Just a minute. So, my claim is that this set is linearly independent. V, TV, Tk minus 1V and alpha 1 to alpha R, right? For some R here. So, if you take, say, lambda 1V plus lambda 2TV dot 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 lambda k t k minus 1V and lambda k plus 1, oh maybe say take c1 to ck, c1 alpha 1 up to cr alpha r such that this is 0. No, let's do this way. Let alpha belongs to V. Okay, so T alpha, so if T alpha is 0, then alpha belongs to kernel T. Otherwise, if T alpha not equals to 0, wait a minute. Rahul, can you help me out? Wait a minute, this is taking very long. So I am stating the claim here. We will try to prove this. T is nilpotent. Then rank of T is equal to the degree of minimal polynomial this is my claim. Okay, we will try to prove this. Okay, please remind me, please. মনে করছ তো কেউ এটা? This is the projection operator. Try to see the minimal polynomial of this. Okay, this will be this. Okay, I am just stating it, you can check it out. Just evaluate the matrix with respect to the usual basis. Let A be an n-cross-n matrix with characteristic polynomial this, show that the trace is this. Oh my lord, this is again a very tedious calculation. But this is obvious now, because sum of the roots is trace. Do you know that? Do you know that sum of the eigenvalues is basically the trace of A? Hello. See, this has a very big calculation as well. Let me know, I will send you the solutions. Like this is one of the problems, like those one, like the one we had there in the last chapter. I think we had one, and I am telling you guys to remind me to send these solutions, otherwise these problems will be unattended. Like this one, the solutions are not very tricky, but they are extremely long. So please let me know, I mean remind me, then I will send you the solutions. Please do this. Please try 10. You have 5 to 7 minutes, 5-6 minutes. Please try 10. Is Ognidipto in the class? Okay, so we don't have much left. B be a vector space of n cross n matrices over the field F. Let A be a fixed n cross n matrix. Let T be the linear operator of V. So what they are saying is, so what they are saying is that Mm, hmm. So we all know that we have shown it that t to the power ib is t to the power I minus 1 of tb, that is t to the power I minus 1 of ab, and that is t to the power I minus 2 of t of ab, that is t to the power I minus 2 of a square b, and so on. We have seen that it is a to the power I into b, right? So if say g x is any polynomial in kx, we know that gt acting on b is nothing but ga acting on b, right? ga into b basically. So now let's pt be the minimal polynomial of t and pa be the minimal polynomial of a. Okay, so what is pa of t into b? What is that for any b? First of all, t is a linear map from mnf to mnf. mnf is our v, huh? So pa t of b is pa a into b, right? But this is 0, no? Because pa is the minimal polynomial of a. So what do you get? pa annihilates t, thus pt x divides px, right? Again, pa pt of t of b is, this is 0 equals to, because pt of t is 0, na, because pt is the minimal polynomial of t, this is pt of a is equal to b, right? For any b. Okay, so pta is a matrix such that pta into b is 0 for all, I mean this is into 0 for all b belongs to mnf. Can you prove that pta is basically 0? That if, I am trying to prove this, that if cb is 0 for all b belongs to mnf, a matrix, then c equals to 0. Can you prove it? Okay, so this is a homework. Try to do it. If you can't do it, then let me know. I keep giving you homeworks and you keep on not doing them. So PTA is 0. That implies PAX divides PTX. Okay, so PX equals to PTX. So A be the vector space of n cross n matrices over the field F. Okay, let A be a fixed n cross n matrix. Oh, we just did it. Let A be a n cross n matrix over the field F. According to exercise 9 of section 1, matrix AB and matrix BA have same characteristic values, right? We have done this. Exercise 9 of section 6.1. Remember, there was a problem which said if AB minus I is invertible, then BA minus I is invertible if and only if not equals to 0, if and only if this not equals to 0. This is, they are talking about that problem. Do they have the same characteristic polynomial? Do they have the same minimal polynomial? What do you think? AB and BA have same characteristic values. Do they have the same minimal polynomial and same characteristic polynomial?
कैरेक्टरिस्टिक पॉलिनोमियल तो सेम ही हो गया।
Why?
मैं যেভাবে অঙ্কটা করেছিলাম না, আগে দাঁড়াও।
Yeah, find the problem and give me 1 minute. Just give me 1 minute. Let me check that whether I will lock the main door or not. So what do you think? Do they have the same minimal and characteristic polynomial? Hmm. So same. BA and AB have the same characteristic values.
আইগেন ভ্যালু গুলো তো সেম হয় না,
Yeah, but
তো
the
ক্যারেক্টারিস্টিক
multiplicities.
সেম হবে।
Should the multiplicities be same as well?
ডিটারমিনেন্টের প্রপার্টি থেকে কি
Let me think. let's first give a counter example.
এই দুটোকে আমরা সিমিলার ম্যাট্রিক্স দেখাতে পারি, তাহলে তো
Yeah, but actually that's very tough because you don't know whether A is invertible or not.
রিয়েল আর নট। হ্যাঁ, এটাও পয়েন্ট।
Who is talking, by the way? Ritik, na? Who was it?
আমি সায়ন দাদা।
Actually, I'm yet to be familiar with your voice. It will take a while. Okay, so let's do this. Take A equals to 1 0 0 0 and B equals to 0 1 0 0. So AB becomes 0 1 0 0 and BA becomes 0 0 0 0. So minimal polynomial of this is x and minimal polynomial of this is x square. So AB and BA need not to have same minimal polynomial. Okay. Now we are going to use a trick to do this part. For the characteristic polynomial, define C to be lambda into identity plus A. This is identity of A. Okay. B I. Okay. Clearly this is a 2n cross 2n matrix. Okay. And D is minus I 0.
IN.
Yeah, IN. Lambda IN. That is identity matrix of order n. Minus lambda IN. Okay. This is again a 2n cross 2n matrix. These are block matrix. Hope you understand that. I have written the matrices in blocks. So what is CD? What is CD? CD is minus lambda IN plus AB minus lambda E. Please check the calculations. I am computing CD. Okay, and this is 0 minus lambda I, right? And what is DC? DC is minus lambda I minus A 0 BA minus lambda I. Now determinant CD, that is equals to determinant DC, na? Right? So what is determinant CD and what is determinant DC? See that determinant DC is this into this, that is determinant lambda IN into AB minus lambda IN, that is equal to determinant minus lambda IN into determinant BA minus lambda IN, right? Right. You cancel these two parts. Yes. AB minus lambda IN is the determinant BA minus lambda IN. Okay. So that is the characteristic polynomials are equal. Okay. Characteristic polynomial for AB is equal to the characteristic polynomial for BA. Okay. Invariance of spaces, just let me have a look at it. How long? T conductor. So this the big chapter. Okay, we will do it in the next class. Today is it's getting very late. But we were stuck at 9, no? We were stuck at 9. What we couldn't do? What was that problem that we were struggling to do? It was 9, no?
ওই যে এক্স টু দি পাওয়ার এন কেন হবে এটা?
No, that is 1. See each polynomial since minimal polynomial. See, the problems, those are not happening right now. Please let me know so that I can send it. Like I have found the solution for question number 9. I am sending it to you. Okay, so that's it for today.